Hello friends, welcome back to my YouTube channel. Today in this video, I will be talking about the maximum strain energy theory. So this is a part of my discussion on high pressure vessels, and since last few videos, I have been talking about the theories of elastic failure. Till now, I have discussed the maximum principal stress theory, the maximum shear stress theory, the maximum strain theory, and today I'll be talking about the maximum strain energy theory. So this theory, it accounts for elastic failure in materials. So why we need to know about the theories of elastic failure? The reason is these theories, they are used in the design of high pressure vessels. And that's why I have included this as a part of my discussion on high pressure vessels. So the design of high pressure vessels, it is based on the theories of elastic failure. As far as elastic failure is concerned, elastic failure in a material, it occurs when it is subjected to a load that exceeds its elastic limit. When the elastic limit of a material is crossed beyond the elastic limit, the material gets permanently deformed or permanently ruptured. Many theories have been proposed to account for elastic failure in material. We call these theories as the theories of elastic failure. Four important theories of elastic failure. You have maximum principal stress theory, then you have maximum shear stress theory, maximum strain theory, and finally you have maximum strain energy theory. First three theories I have already discussed in my earlier videos. I am giving link to those videos in the description section. You please watch those videos if you have not yet seen them. Okay, so let us today talk about the maximum strain energy theory. What is this theory? Let us understand. Maximum strain energy theory. According to this theory, according to the maximum strain energy theory, failure in a material will occur if the strain energy accumulated in the material becomes equal to the strain energy at the elastic limit. And this elastic limit is taken as the yield point of the material. Okay, so as per this theory, if the strain energy accumulated in the material under the influence of applied load, it becomes equal to the strain energy that would be accumulated at the elastic limit. And if this happens, then the material is going to fail according to this theory. In this case, the elastic limit is taken as the yield point. So the theory says failure in a material will occur if the strain energy accumulated in the material becomes equal to the strain energy at the elastic limit. The elastic limit is taken as the yield point of the material. Yield point is a point beyond which the material begins to plastically deform. Below the yield point, material will be elastically deformed. That means it will be regaining its shape and size after the removal of applied load. Now, what is the strain energy? Strain energy is the mechanical energy absorbed by the material when it is stressed. So, any material, if it is stressed, it absorbs some mechanical energy, and we call that energy as the strain energy. It is given by this equation. UCR is equal to 1 upon 2E into sigma C square plus sigma R square minus 2 mu into sigma C into sigma R. Again, I am directly taking this equation in my discussion, and I am going to use it in order to understand the maximum strain energy theory. Okay, so the mechanical energy, if any material is stressed, then the mechanical energy absorbed by it, that is the strain energy in the material, It is given by this equation. UCR is equal to 1 upon 2E into sigma C square plus sigma R square minus 2 mu into sigma C into sigma R. In this case, E is the modulus of elasticity, sigma C is the circumferential stress, sigma R is the radial stress, mu is the Poisson's ratio. So sigma C is the circumferential stress and radial stress. If you have to know more about them, I have discussed them in my earlier videos. You please watch those videos. So the strain energy is given by this equation. UCR is equal to 1 upon 2E into sigma C square plus sigma R square minus 2 mu into sigma C into sigma R. And sigma C, the circumferential stress, is given by this equation. Sigma C is equal to A plus B upon R square. Here I am using the equation in terms of constants A and B. So I have discussed in details about these constants and how to get values for these constants in my earlier videos. So let me take the equation in terms of constant. So in terms of constants A and B, the circumferential stress at any radius R that gets induced in the wall of a high pressure vessel, it is given by this equation. Sigma C is equal to A plus B upon R square. And then likewise sigma R will be given by this equation. Sigma R is equal to A minus B upon R square. Again, I have considered this equation with the sign convention. And what is the sign convention? Tensile stress is considered to be positive and the compressive stress is considered to be negative. In this case, circumferential stress, that is sigma C, is tensile and hence it is positive, and the radial stress, sigma R, is compressive and hence it is negative. And I have considered this equation by taking that into account. That means with the sign convention, equation for sigma R is A minus B upon R square. A and B are constants and R is any radius of the cylindrical vessel. So therefore you have UCR is equal to 1 upon 2E. I'm using equations for sigma C and sigma R. So you get UCR is equal to 1 upon 2E into 1 plus A plus B upon R square plus A minus B upon R square minus 2 mu into A plus B upon R square into A minus B upon R square. Now I will deal with each term separately. For example, A plus B upon R square. If you take square of this, it would be A square plus 2 into A B upon R square plus B square upon R raised to 4. So I have used in this case this equation. For example, m plus n square, it will be m square plus 2mn plus n square, and I have used this equation to expand the square of this term A plus B upon R square. Now let us open that. Similarly, A minus B upon R square, it will be A square minus 2 into A into B upon R square plus B square upon R square. Over here I have used this formula. M minus n square is m square minus 2 into m into n plus n square. So using this I have expanded this bracket. A minus B upon R square, square of that. So this is A square minus 2A into B upon R square plus B square upon R raised to 4. And if you add this 2, so it would be A square plus A square that is 2a square plus 2a into b upon r square minus 2a into b upon r square. The two terms will get cancelled, and b square upon r raised to 4 plus b square upon r raised to 4 is 2 times of b square upon r raised to 4. That means the addition of these two terms, a plus b upon r square plus k minus b upon r square, it is simply 2 into a square plus 2 into b square upon r raised to 4. So the strain energy is UCR is equal to 1 upon 2E 1 plus b upon r square plus 1 minus b upon r square minus 2 into mu into a plus b upon r square into a minus b upon r square. And we got the result of addition of this two term. A plus b upon r square plus a minus b upon r square is 2a square plus 2b square upon r raised to 4. So let us use it. So UCR is equal to 1 upon 2e into 2a square plus 2b square upon r raised to 4 minus 2 mu into a square minus b square upon r raised to 4. How is this term obtained? Now this is product of, if you look at this product, this is equivalent to m plus n into m minus n. So product of these two brackets is simply m square minus n square. So I have used this formula over here. So that is, you get a square minus b square upon r raised to 4. Therefore, UCR is equal to 2 upon 2e 2 into a square plus b square upon r raised to 4 minus mu into a square minus b square upon r raised to 4. So 2 is taken out of the bracket because it is present in every term. Then UCR is equal to 1 upon e, 2 will get cancelled, into a square plus b square upon r raised to 4 minus mu into a square plus mu into b square upon r raised to 4. So mu is multiplied with each term in the bracket. You get this. So the strain energy is given now by this equation. UCR is equal to 1 upon e into a square plus b square upon r raised to 4 minus mu into a square plus mu into b square upon r raised to 4. That is, UCR is equal to 1 upon e into 1 minus mu a square plus 1 plus mu b square upon r raised to 4. So what is done? From this term and this term, we take a square common. So you are left with 1 minus mu into a square. Then from this term and this term, you take b square upon r raised to 4 common. So you get this 1 plus mu into b square upon r raised to 4. Further, let us use now the equations for constants. So how these equations are obtained, I have discussed in my earlier video. So A is equal to pi ri square minus po ro square upon ro square minus ri square. Pi is the internal pressure, po is the external pressure, I is the internal radius of the vessel, cylindrical vessel, and ro is the external radius of the cylindrical vessel. And B is given as r square into ro square into ri square divided by ro square minus ri square into pi minus p naught. I have discussed how these two equations are obtained in my earlier video. You please watch those videos. Okay. So if you consider PO to be 0, that is external pressure to be 0, which is true for almost every high pressure vessels, then A will be pi ri square minus PO is 0. So minus 0 into ro square divided by ro square minus ri square. That is nothing but pi into ri square upon ro square minus ri square. and B will be RO square into RI square divided by RO square minus RI square into PI minus 0, because PO is 0. So that gives us RO square into RI square into PI divided by RO square minus RI square. And if you use these equations, you get UCR is equal to 1 upon mu E into 1 minus mu into Pi square Ri raised to 4 into RO square minus Ri square and square of that. So if you are using equation for A, here it is A square. So I have to square this term. So that's why you have this term. Plus 1 plus mu. 1 plus mu, it is B squared. So I have squared this equation. So that gives me R raised to RO raised to 4, Ri raised to 4, Pi square divided by RO square minus Ri square, square of that term into R raised to 4. I get this equation because you have square of B and R raised to 4 is already there in the equation. So I'll find at the end you are getting this equation for the strain energy. So we got this equation for the strain energy. UCR is equal to 1 upon E into 1 minus mu into Pi square Ri raised to 4 divided by RO square minus Ri square, square of that term plus 1 plus mu into RO raised to 4 Ri raised to 4 Pi raised square divided by RO square minus Ri square, square of that into R raised to 4. Now if we want to have the strain energy at the inner surface, that means when R is equal to Ri. So that gives us UCR is equal to 1 upon E into 1 minus mu Pi square into Ri raised to 4 divided by RO square minus Ri square, square of this plus 1 plus mu into R raised to 4 Ri raised to 4 Pi square divided by RO square minus Ri square, square of this into Ri raised to 4. So now we have replaced R with Ri because this is true at the inner surface. So this simplifies the equation to this form. UCR is equal to 1 upon E into 1 minus mu Pi square into Ri raised to 4 RO square minus Ri square, square of this plus 1 plus mu into Ri raised to 4 and Ri raised to 4. This are going to get cancelled. So you are left with 1 plus mu into RO raised to 4 Pi square divided by RO square minus Ri square in square of that. Further, UCR will be equal to Pi square because Pi square is present in both the terms. So we are going to take it out of the bracket. So it will be Pi square upon E into 1 minus mu Ri raised to 4 plus 1 plus mu RO raised to 4 divided by RO square minus Ri square and square of that term. Okay, so we got the equation for strain energy. UCR is equal to Pi square upon E into 1 minus mu Ri raised to 4 plus 1 plus mu RO raised to 4 divided by RO square minus Ri square, square of this. Now let us replace radius with diameter because the radius is half of the diameter. For example, internal radius, that is Ri, will be di by 2 and the outer radius will be do by 2. So if you replace, if you do this replacement, you get this equation. UCR is equal to Pi square upon E into 1 minus mu di upon 2 raised to 4 plus 1 plus mu do upon 2 raised to 4 divided by do upon 2 raised to 2 minus di upon 2 raised to 2 and square of this. Okay, if you look at this term, this will be di raised to 4 upon 2 raised to 4, do raised to 4 upon 2 raised to 4. do square upon 2 square minus di square upon 2 square, and if 2 square comes out, it will be 2 raised to 4. The meaning is 2 raised to 4 is present in the numerator in each term, and 2 raised to 4 is also present in the denominator. That's why this 2 raised to 4 will be cancelled, and you are left with UCR is equal to pi square upon E into 1 minus mu into di raised to 4 upon 2 raised to 4 plus 1 plus mu upon do raised to 4 upon 2 raised to 4 divided by 1 upon 2 raised to 4 into do square minus di square of that. So 2 raised to 4 is present in the numerator, and 2 raised to 4 is also present in the denominator. So it will get cancelled out. So with this, the strain energy equation will be UCR is equal to pi square upon E. Previously we got this into 1 minus mu di raised to 4 upon 2 raised to 4 plus 1 plus mu do raised to 4 divided by 2 raised to 4 divided by 1 upon 2 raised to 4 do square minus di square of that. So 1 upon 2 raised to 4 will be getting cancelled, and you are left with UCR is equal to pi square upon E into 1 minus mu di raised to 4 plus 1 plus mu do raised to 4 divided by do square minus di square of that. Now the strain energy at the elastic limit. So this is the strain energy that is getting induced in the material under the influence of circumferential and the radial stresses. Now let us talk about the strain energy at the elastic limit. The strain energy at the elastic limit, or you can say at the yield point, is given by this equation. Uy is equal to sigma y square upon 2E, where sigma y is the yield stress. E is the modulus of elasticity. And according to this theory, if the strain energy in the material, that is UCR, becomes equal to the strain energy at the elastic limit, the material is going to fail. So according to this theory, it is UCR is equal to Uy. UCR, we got this equation for UCR. So I have, that is nothing but Uy is equal to UCR. Okay. So if we use the equations, Uy is sigma y square upon 2E and UCR is this equation, pi square upon E into 1 minus mu di raised to 4 plus 1 plus mu do raised to 4 upon do square minus di square of that term. So that gives us sigma y square as 2 into pi square into 1 minus mu di raised to 4 plus 1 plus mu do raised to 4 divided by do square minus di square of that. So what is happening over here, E and E, they will get cancelled because E is present on both the side and this 2 is taken to the other side. So you get this equation for sigma y square. So according to the theory, you got this equation, sigma y square is equal to 2 into pi square into 1 minus mu bi raised to 4 plus 1 plus mu do raised to 4 divided by do square minus di square of that term. Therefore, sigma y square is equal to 2 into pi square. I am taking di, or I am dividing numerator with di raised to 4 and denominator with di raised to 4. So it will be 1 minus mu di raised to 4 divided by di raised to 4 plus 1 plus mu do raised to 4 upon di raised to 4. And if I divide in the numerator, in the denominator, if I divide with di raised to 4, and if di raised to 4 is taken into the bracket, it will be di raised to square. And because you have square over here, so a term will be like this, do raised to do square upon di square minus di square upon di square. So what is going to happen? di raised to 4, di raised to 4, it will become 1. Do raised to 4 upon di raised to 4, this will be k raised to 4, because if I replace do upon di with k, it will be k raised to 4. Similarly, here over here it will be k square, di square upon di square, it will become 1. So that's why equation for sigma y square will be 2 into pi square into 1 minus mu plus 1 plus mu k raised to 4 divided by k square minus 1 square of that, where k is nothing but, in this case, k is the ratio of outer diameter to inner diameter. K is du upon dl. So that gives us sigma y as square root of 2 into pi square into 1 minus mu plus 1 plus mu k raised to 4 divided by k square minus 1 square of that. That is sigma y will be equal to, so you can take pi square, it can come out of the square root, so it will be pi, and then k square minus 1 square, it will come out. So that's why you have pi upon k square minus 1 into under root of 2 into 1 minus mu plus 2 into 1 plus mu into k raised to 4. So this is the condition at which failure is going to occur in the material according to the maximum strain energy. Now let us talk about the design equation, the equation that can be used to get the diameters and thickness of high pressure vessels. So from the previous discussion, you got sigma y is equal to pi upon k square minus 1 into under root of 2 into 1 minus mu plus 2 into 1 plus mu k raised to 4. So for the design purpose, we are going to use a factor of safety, that is Fs, so that the induced stress will be less than sigma y. So that means we are going to divide sigma y with Fs. So that will give us sigma y upon Fs is equal to pi upon k square minus 1 into under root of 2 into 1 minus mu plus 2 into 1 plus mu k raised to 4. That is sigma y is equal to Fs into pi upon k square minus 1 into under root of 2 into 1 minus mu plus 2 into 1 plus mu k raised to 4. So this equation we will be solving to get k. The equation has to be solved for k because all other values, that is sigma y, Fs, pi and mu, they will be known to us, and you can easily solve this equation to get the value of k. So what is k in this case? K is nothing but the ratio of outer diameter to inner diameter. Okay, so you are going to get k by using this equation. Di will be provided to you, so you can easily get du. And then once du and di are known to you, then you can get the thickness of the vessel. So I can show over here. So this is the internal diameter. This is the thickness of the vessel. Again, this is the thickness, and this is the outer diameter, that is du. That means du is ts plus di plus ts, that is du will be equal to di plus 2 into ts. So you can simply use this equation to get the thickness. So in this way, by using maximum strain energy theory, you can get internal diameter, external diameter and thickness for high pressure vessels. And in this way, you have to use the theory to design the high pressure vessels. So with this, I end my discussion for this theory, the maximum strain energy theory. I hope you have understood the theory, and in this way I complete my discussion on theories of elastic failure. In my next video, I will discuss one numerical where we will be using all the 4 theories to design high pressure vessels. Thanks for watching my video. Do subscribe to my channel. Tell your friends to subscribe to it, and don't forget to hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. So for now, thanks. Have a nice day and hope to see you soon in my next video.